The great advance of quantum mechanics was its ability to explain the electronic structure of atoms, namely the quantized energy states and the sp and d orbitals we use in chemistry. We can apply the Schrödinger equation to the atom by considering the Coulombic attraction between the negatively charged electron and the positively charged nucleus. The Coulombic potential is inversely proportional to R, where R is the separation between the electron and the nucleus. The potential is negative because the force is attractive with the negatively charged electron desiring to be close to the positively charged nucleus. Here Z is the number of protons in the nucleus, where Z is 1 for a hydrogen atom. Because the Coulombic force and potential depend only on the distance r between the nucleus and the electron, and not the angle, spherical coordinates will best describe the position of the electron. We will put the nucleus at the origin of our coordinate system. Theta represents the angle between the r vector and the z-axis, and phi represents the orientation of the electron around the z-axis. Using this coordinate system, the potential term in our Schrödinger equation depends only on r and not theta and phi. To solve the problem, then, we will need to use the divergence, which is the second spatial derivative in spherical coordinates. Before we do the math, we can get a good idea about what wave functions we expect for an atom by using our knowledge of the particle in a box and tunneling. By setting v equals 0 as the potential at infinity, any electron with positive energy will be able to escape the atom, whereas any electron with negative energy will be bound to stay near the atom. We found that free electrons are not quantized, while bound electrons should have quantized states similar to what we found in the particle in a box. Thus, we will be interested in finding the quantized bound states for energies less than 0, and we expect to find 3 quantum numbers like we did for the 3D box, based on the boundary conditions from r, theta, and phi. We expect that our lowest energy wave function, or E equals 1 state, to be the smallest wave that fits within the bounds as we found with the particle in a box. So for our ground state energy, say here, we expect that our ground state wave function for energy greater than V should look something like that. From our experience with tunneling, we know that we expect wavy curvature when energy is greater than the potential, but exponential decay when energy is less than potential. So we expect that at large r, our wave functions will decay exponentially. Notice that we drew our wave function with continuous first and second derivatives, but because the potential at r equals 0 is minus infinity at the nucleus, we don't really expect the first derivative to be continuous there. So we shall change our wave function guess a bit and draw our wave function with a bit of a cusp. As we move to higher energy, we expect degenerate states to appear due to the symmetry, and then we expect that the number of states to grow rapidly as the confinement vanishes. The wave function of the first excited state should have one node symmetrically placed in the center, like we found in a particle in a box. We can expect that the wave function looks like the first excited state of particle in a box when E is greater than V, and then exponential decay outside. We shall see that this guess is pretty good for the excited P state, but the excited S state will look a little different. The mathematical solution to the Schrödinger equation is found using separation of variables, as we found before for other problems. Here, the wave function is separated into a radial wave function depending only on the variable r, and an angular wave function depending only on the variable theta, and another one depending only on the variable phi. As we expected, the boundary conditions give us 3 quantum numbers, which we call n, l, and m sub l, with n being the principal quantum number, determining the distance r, which also determines the energy. The orbital angular momentum quantum number L will lead to quantization of angular momentum and further degeneracy of the states with primary quantum number n, while the magnetic quantum number m sub L will add further degeneracy by describing the orientation of the angular momentum along a particular axis, in this case the z-axis. We identify different electronic states with the principal quantum number n, but use S, P, and D instead of the L value. The magnetic quantum number then gives degeneracy 1 to S states, 3 to P states, 5 to D states, and so on. Let's take a look at some of these spherical harmonics that depend only on theta and phi angles in our spherical coordinates. When m equals 0 and L equals 0, the spherical harmonic function is simply a constant. And so our spherical harmonic is spherically symmetric. When m equals 0 and L equals 1, the spherical harmonic depends on cosine of theta. Theta equals 0 along z, and so cosine of theta is 1, and cosine of theta then decreases as theta moves towards pi over 2 at y. Within the xy plane, cosine of theta is 0, and then cosine of theta becomes negative as we move to the minus z direction. These positive and negative lobes describe the pz orbital or wave function, whereas the spherically symmetric orbital describes an s orbital. The px and py orbitals look similar, where px is actually a linear combination of the m equals 1 and m equals minus 1 spherical harmonics, both with L equal to 1. Representations of the spherical harmonics shown here show positive wave function as blue and negative wave function as yellow. The S states are spherically symmetric, and the three degenerate P states have one planar node perpendicular to either the x, y, or z directions. The D states have L equal 2 and therefore have two planar nodes, and because m can have 5 values for L equals 2, there are 5 D states. Remember that the probability distribution is proportional to the square of the wave function. The probability densities look similar to the wave functions, but both lobes are positive. The 1s orbital of hydrogen is spherically symmetric and a simple exponential as a function of r. This provides a wave function cusp at the nucleus, as we suspected. For the two p states, there's a planar node at r equals 0 that we found previously. Then the wave function rises to form the lobe and then falls exponentially as we predicted. The n equal 2 or 2s wave function again has its maximum intensity at the atom, but that drops rapidly to form a spherical node within the atom itself before then decaying exponentially. While the square of the wave function gives the probability per unit volume, there is more volume at a given r for large r rather than at small r. Thus, the probability of finding the particle at a given r should be scaled with r squared. If we then plot r squared times the square of the radial function, we then get the radial probability density. We then have the probability of finding the electron at the nucleus small compared to other distances, and we also find a distance where you're most likely to find the electron. For the 2p wave function, we get a similar looking curve, although the electron is further out, and the 2s is slightly more extended than the 2p with its node present. As we found in particle in a box, wave functions with more curvature and more nodes have higher energy. Here we show a slice through the probability density distribution function of S states. Remember that the S states have L equals 0 and that the angular functions are only a constant, which means the wave functions are spherically symmetric. The n equals 2 wave function will have a node at r equals 2 times the Bohr radius that we see here due to a minimum in probability before the exponential decay. The n equals 2 function has a smaller factor in the exponent, which makes the wave function larger. For n equals 3, the wave function is even larger, with now 2 nodes. The bound state energies we found from solving the Schrödinger equation are negative, and depend on the charge of the nucleus squared, z squared, divided by the principal quantum number, n squared. Combining all of these constants together comes out to 13.6 electron volts, sometimes called a Rydberg, and will be useful in comparing the energies of these different energy states. The lowest energy or ground state of a hydrogen atom comes out to minus 13.6 electron volts. This is the energy to ionize the hydrogen atom to a hydrogen ion by bringing the electron to V equals 0, which is the continuum of electronic states, the electron here being free and not bound to the proton. A large increase in energy is needed to get to the first excited state, or n equals 2, whereas successively higher energy states are more closely spaced. It turns out that electrons, as well as other quantum particles, inherently have angular momentum that we call spin. Spin and spin quantization is a result of relativistic quantum mechanics. Remember, in relativity, time is combined with the three spatial dimensions to make a four-dimensional space-time. We like to draw an electron as a spherical object spinning on its axis that gives its angular momentum. But it is better to consider spin as an inherent property of an electron or quantum particle, because it is not really spinning. The magnitude of the spin angular momentum s, as well as its z component, m sub s, is quantized. For electrons, this spin value is 1/2. In summary, quantum mechanics gives us four quantum numbers for the electronic states of an atom. The principal quantum number, or n, can be any integer, and this quantizes the electron's energy. The orbital angular momentum quantum number, which can be an integer value up to n minus 1, quantizes the magnitude of the angular momentum. The magnetic quantum number, m sub l, which is limited by the value of L, quantizes the orbital angular momentum along a particular direction. And then the spin quantum number can be plus or minus 1/2. The quantum mechanical requirements of electrons as fermions will require that all electrons on the same atom have a distinct set of quantum numbers. Because of this, we will show only 2 electrons per orbital determined by n, l, and m sub l, where those 2 electrons are due to the 2 spin states allowed.